Hello class 12. The topic that we're going to discuss today is interference of light. But before we jump into interference of light, let us talk about interference of waves. Because interference in itself is a phenomenon exhibited by waves. Alright? So, say we have still water, okay, and we disturb the water at some point. Water in a bowl, or water in a lake, still water, and we disturb it. Alright, so what happens is when we disturb at some point on the water surface, what happens is ripples are generated. Those ripples are what? Those ripples are basically transverse waves. Alright, now what we do is, say now we disturb at two different points. When we disturb the still water at two different points, waves are generated from both the two sources of disturbance, so to say. And those waves, in turn, the waves that are coming from two different sources, they superpose with each other. Alright? And thereby what happens is we get a resultant wave. Okay? So, this phenomenon of superposition of waves and thereby we getting a resultant wave is what is called interference of waves. The amplitude, remember, of the resultant wave can be greater than the amplitude of any one of the initial waves, okay, interfering waves, can be lesser than the interfering waves, the amplitude of the interfering waves, or can be zero also. Okay, so this phenomenon of waves interfering with each other and thereby we getting a resultant wave having a greater amplitude, or could be a lesser amplitude, or could be zero amplitude, is what is called interference. Okay, this can be seen in water also. Now there are many videos in YouTube also. There are videos in YouTube which shows interference of water waves, showing you pattern of interference of water waves. Alright. So I will share you the link of some of the videos also. You can check, interference of water waves in YouTube yourself also. Now this is one picture that I've tried to draw. Say this is water, okay? You disturb the still water at some point and thereby what you get is you start getting ripples in all directions, of course. I've only drawn this portion, of course. So the solid line depicts the maximum. Since ripples are transverse waves, so the solid line depicts the maximum or the crest, and the broken lines, they depict the minimum or the trough, so to say. Okay, so we have two slits over here. So when we disturb the water surface, ripples are generated, and say for example we place a cardboard over here, such that there are two small holes on the cardboard. These two small holes over here. These two small holes are, so to say, equidistant from the main source of disturbance. So this hole, this distance and this distance are one and the same. Now what happens is, when these ripples, they hit these two slits, these two small holes. Now these two small holes, they act like two different sources now. Two different sources of disturbance. So to say, this will generate its own ripples and this will generate its own ripples. Okay, own waves. Now what happens is, in turn, the waves that are generated by these two sources, they interfere with each other. And these points that I have marked by white lines, okay, by white color here. At these points, what is happening is either a solid line is meeting another solid line at these points, also at these points, or a broken line is meeting another broken line. Okay, so wherever a crest, so to say, is meeting another crest, you get a bigger crest. And whenever a minimum or trough, so to say, meets another trough, you get a bigger trough. Alright, so these are the points in the picture where a solid line is meeting another solid line, or a broken line is meeting another broken line. But there are also points like these points here. My picture may not be very clear, okay, but that is exactly what I have tried to depict over here. Now these are points where a solid line is meeting broken line coming from another source. Okay, so to say, a crest or a maximum is meeting another minimum. So when a maximum meets another minimum, what happens is they cancel each other out and we get a 0. So at these points, we are getting 0, so to say. No amplitude whatsoever of the resultant wave, so to say. Okay, now if we place a screen at some point, alright, so if we place a screen, what happens is at these straight lines, at these points where we are getting a maximum, okay, crest meeting another crest or throw meeting another throw, okay, so the resultant amplitude is bigger, so to say. So I'm calling that maximum. So these points are maximum, and when you place a screen at this point, we are going to get a maximum. These are points we are getting a minimum or 0. You know, minimum means where a crest meets another throw, they cancel each other out and we get a minimum. So these are points we are getting a minimum. Alright, so when we place a screen on the screen, this will be the point where we get a minimum. Likewise, these are points where we are getting a maximum, so this will be maximum, this will be minimum, this will be a point where we are getting a maximum. So we'll get this kind of a pattern on the screen, alternate maxima and minima. Alright, so on the screen, this is what we are getting, alternate maximum and minimum, and this is a result of interference of waves. Okay, now coming back to the topic, which is interference of light. What has been seen is, talking about light, the exactly same kind of thing has been seen in case of light also. If this is considered to be a source of light, alright, and this source of light is giving out waves, since we are considering light to be wave here. Okay, now this wave is blocked by a cardboard where we place two small holes, again, two slits, so to say. These two slits are equidistant from our main primary source. Now, according to Huygens principle, these two slits also act as two different sources of light. So every point lying on this slit is a new source of light, every point lying on this slit is a new source of light, and thereby what we get is, we get these two slits, so to say, if we observe from this side, these two slits, they act as two different sources of light. Okay, so waves thereby coming from these two sources of light, they interfere with each other, okay, in turn giving us alternate maximum and minimum. Okay, wherever we get a maximum, that particular point is called, that is the point we get as a result of, so to say, constructive interference. Now we are using technical terms. Constructive interference means the point we get constructive interference wherever a maximum, a crest meets another crest, or a throw meets another throw. Okay, whereas we get destructive interference, we get a 0 at points wherever a crest meets another throw. Okay, so you need to understand this very clearly. Constructive interference means crest meeting another crest, or a throw meeting another throw, whereas destructive interference means the opposite, crest need not be the opposite, okay, but a crest meeting another throw. So wherever a crest meets another throw, we get destructive interference. Now, so this phenomenon, so to say, of interference is exhibited by light also. Therefore, light is considered to be a wave. Okay, so we get to see alternate constructive interference and destructive interference, or so to say, another technical term we use, we get alternate bright and dark fringes. Okay, small portions are called fringes here. Okay, so we get, so to say, alternate. So on the screen, if you place the screen, what we get to see is, on the screen we see a pattern like this. So this will be bright, then alternate we will get to see dark, bright, this will be dark, this will be bright. So we'll get a pattern like this on the screen. So we get these portions, these lengths are called fringes. So we get alternate bright and dark fringes, alternate bright and dark fringes. At the central point over here, of course, what we get to see is we get a bright fringe. Okay, and then after we'll get alternate bright and dark fringes. Like this. Alright, so this phenomenon of interference of light therefore proves that light is a wave and not a particle, because as I've already told you earlier, interference is a phenomenon exhibited by waves and not particles. So therefore this proves that light is a wave. Now, talking about the example of interference of light that we see in our daily life is, if we have a soap bubble and it's a sunny day, soap bubble, we can see different colors, on the soap bubble. Now, that is a result of interference of light. Likewise, if oil is spilled on the floor, again, it's a sunny day, then you get to see different colors on that oil. Now, that also is an example of interference of light. Now, specifically, this particular thing, talking about this thing in particular, we have one source of light, a single source of light, and we have two different slits. We have made two different slits, okay, which acts as two different sources of light, and thereby we get alternate bright and dark fringes. This particular thing is called Young's double slit experiment, because this phenomenon of interference of light was actually shown experimentally in 1801 by Thomas Young, and thereby the name Young's double slit experiment. Now, these two alternate sources of light, two slits S1 and S2, are called coherent sources of light. Now, what are coherent sources of light, so to say? Two sources of light are said to be coherent. This is the definition, of course, okay? If they emit light having the same frequency, they are almost of the same amplitude, and they have a constant phase difference between them. Constant phase difference meaning a phase difference which does not change with time. Now, instead of two slits, can we use two bulbs? And can we see waves? Waves will of course come out of the two bulbs. Do we see those two waves interfering? The waves coming from these two bulbs interfering? Now, the answer will be no, because the two bulbs or two tube lights cannot act as coherent sources, because they do not, what happens is the phase difference between them constantly changes. Okay, so therefore two different bulbs cannot act, even if I switch them on at the same time, they do not act as coherent sources. For coherent sources, the phase difference has to remain constant with time. So how did Thomas Young make two coherent sources? What he did is exactly this. You have a source of light, a bulb, alright, and he placed a cardboard, he made two small holes, two slits, and the waves started interfering. And thereby we get alternate bright and dark fringes. Now, for this experiment to hold true, of course, what should happen is, what we should do is, the width of the slits should not be very large. It should be very small, the width very tiny hole. Okay, so such that the width of the slit is comparable to the wavelength of light. Okay, because when the width of the slit is comparable to the wavelength of light, then what happens is, then something called phenomenon of diffraction starts happening. Phenomenon of diffraction becomes true, holds true. Okay, but we will talk about phenomenon of diffraction in another video. Alright, but do remember, the width of the slit should be comparable to the wavelength of light for us to see this interference pattern, that is alternate bright and dark fringes. Okay, so that is exactly what Young did, and thereby demonstrated the phenomenon of interference of light. So this is the definition for coherent sources. You will be asked. So do remember this. Now, important things, which are the conditions for constructive and destructive interference. I say important because these are things that will be asked in the exam. So what are the conditions for constructive interference? Let us look at that first. So the phase difference, if the phase difference between two interfering waves is 0, that is there is no phase difference, they are meeting in phase, or they have a phase difference of 2 pi, 4 pi, 6 pi, that is even number multiple of pi. If the phase difference is an even number multiple of pi, then we get constructive interference at that particular point. Or the very same thing could be said in, or could be expressed in terms of the path difference also. If the path difference x between two interfering waves is 0, that is there is no path difference whatsoever, or lambda, that is one complete wavelength, 2 lambda, 3 lambda, that is an integral multiple of lambda. If the path difference is an integral multiple of lambda, then also what we get is we get a constructive interference. The general way of saying integral multiple of lambda is n lambda, where n is 0, 1, 2, 3. When n is 0, then 0 into lambda gives you 0, 1 lambda gives you lambda, and so on. Likewise, the general way of saying even number multiple of pi is 2n pi. Okay? If these are two slits, so these are the two slits, and this is the screen. Okay, this is the screen. So we have, say we are talking about this particular point, we have a wave reaching there, and we have another wave reaching from the other slit. So these two waves, they interfere at this particular point. So what we are trying to say is, as you can see, this wave starting from the lower slit, lower source of light, so to say, it is traveling a longer distance. So obviously there is some path difference between these two waves, or rays of light, so to say. Now what we are saying is, if this path difference is integral multiple of lambda, okay, then there is, what we get is we get constructive interference, or a maximum, or a bright fringe, so to say, at this particular point. That is exactly, at this center over here. At the central point of these two slits, what happens is a ray of light starting from the upper slit travels this distance. A ray of light starting from the lower source of light, lower slit, also travels the same distance, since this central point is equidistant from the two slits. So the path difference between these two interfering waves, it's 0, because they are traveling the same distance, and thereby what we get is, at the central point we get a bright fringe, we get a maximum, we get constructive interference. Okay, so these are two different ways of saying the same thing, remember. Alright, because remember, a phase difference of 2 pi corresponds to a path difference of lambda. Okay, and a phase difference of phi therefore corresponds to a path difference of x, which is equal to lambda by 2 pi into phi. So this is the formula, this is the relation between path difference and phase difference. Okay, so if phi is 2 pi, then what happens? 2 pi, they divide each other and x becomes lambda. If phi is 4 pi, if this phi is 4 pi, then x will be how much? 2 lambda. Okay, so that is what I am saying. It's two different ways of saying the same thing. So these are the conditions for constructive interference, very, very important. You will be asked, what is the condition for constructive interference? Or you will be asked, what should be the path difference for constructive interference? You might be asked in terms of the phase difference as well. Likewise, conditions for destructive interference. The phase difference phi has to be an odd number multiple of pi. General way of saying that is 2n plus 1 into pi, where n is 0, 1, 2, 3, 4, whatever. Alright, so if n is 0, phi becomes pi. If n is 1, okay, then phi becomes 3 pi. Okay, if n is 2, phi becomes 5 pi, so on. And likewise, another way of saying that is speaking in terms of the path difference. The path difference has to be odd number multiple of lambda by 2. The path difference has to be odd. This is 1 into lambda by 2, 3 into lambda by 2, 5 into lambda by 2, 7 into lambda by 2. Okay, generally we are saying that 2n plus 1 into lambda by 2, where your n is 0, 1, 2, 3, 4. Okay, so to say, if two interfering waves, the path difference between these two interfering waves is lambda by 2 or 3 lambda by 2 or 5 lambda by 2, what happens is, at this particular point we are going to get a destructive interference, because if the path difference is an odd number multiple of lambda by 2, what happens is, at those points a crest will meet a trough. Definitely a crest will meet a trough. Whereas if the path difference is 0, either a crest will meet another crest or a trough will meet another trough. Okay, path difference of 0 or lambda or 2 lambda or 3 lambda, like that. Okay, so these are the conditions remember for constructive and destructive interference. You need to remember this. Now for Young's double slit experiment, let us try calculating the path difference. The path difference between two waves starting from the two slits. S1 is the lower one, S2 is the upper one. Okay, so to say we want to calculate what is the path difference between these two waves starting from S1 and S2 respectively and reaching the same point P. Let us also consider that this point P is distance x from our central point on the screen, which is O. This O, mind you, is equidistant from both S1 and S2 such that at point O, the path difference between the two waves reaching point O from S1 and S2 is 0. Therefore, at point O, we are getting a bright fringe, definitely, mind you. And we want to calculate therefore the path difference between S1P and S2P, so to say. So the path difference is S1P minus S2P. You can see from the picture also that S1P is a bit longer than S2P. Now what we've considered is the slit width, or also called slit separation, that is this distance. S1, the distance between S1 and S2 is D. This small d that is, okay? And capital D is the distance between the screen and the two slits. So this distance is capital D. Capital D is much greater than our small d, do not forget that. Not slow, okay? The slit separation is very small. Okay, the width of the slit itself is, the slits are very, very tiny holes, okay, and the separation between the two slits, the slit width, which is called, is very small. And OP, like I've already told you, OP is x, and capital D is the distance between the screen and the two slits. So if that's the case, we want to calculate S1P minus S2P. Before we jump into this, let us calculate this S1P squared minus S2P squared. Okay, now what is S1P squared? S1P squared is the thing inside the curly bracket. Why? Because S1P is the hypotenuse of this triangle. PS1, let me see, this is A. PS1A. Look at triangle PS1A, this right angled triangle. Okay, so S1P is the hypotenuse of triangle PS1A. So this, using Pythagoras theorem, of course, H squared is P squared plus B squared. So our B is D, capital D. So base squared plus perpendicular squared. Perpendicular, this distance is x. So what is this distance OA? The distance OA is the half of the slit separation. The slit width is D. So this half of D is D by 2. So this OA is D by 2. Likewise, this distance, let me call this B. This point over here. OB will also be D by 2. So therefore, what is PA? PA is x plus D by 2. Alright, therefore S1P squared is D squared plus x plus D by 2 all squared using Pythagoras theorem. Likewise S2P. S2P is the hypotenuse, S2P is this, is the hypotenuse of the triangle PS2B. Okay, so the hypotenuse squared is perpendicular squared plus base squared. So the base squared is D squared plus perpendicular. What is PB? PB is x, this PO is x minus OB. So x minus OB, OB is D by 2. So x minus D by 2 is your distance PB, and thereby S2P square is d squared plus x minus d by 2 whole square. Now a square, this is in the form a squared minus b squared. A squared minus b squared is a plus b into a minus b. That is exactly what I've written. So this is the left hand side, and the right hand side I expand it. So d squared is d squared. So x plus d by 2 whole square, I've opened it in the formula a plus b whole square. So a squared plus b squared plus 2ab. So up to here is the thing from the first curly bracket minus second curly bracket. I've opened it straight away. So d squared, you can check the mathematics. D squared plus a minus b whole squared is a squared. Okay, you can check the mathematics. So d squared, x squared, d by 2 whole squared, d by 2 whole squared, they cancel each other out, and what adds up is 2x d by 2. This is simply xd. This is also xd because 2 they divide each other out. So xd becomes 2xd. Therefore, S1p, the left hand side, S1p minus S2p, this thing I've taken it to the right hand side. So what we have in the right hand side from here is simply 2xd. So 2xd divided by S1p plus S2p. Please check the mathematics yourself. And thereby S1p minus S2p becomes 2xd divided by 2 capital D. Now, where do we get this from? What we've done is we've approximated over here this denominator. Now see, since capital D is much greater than small d, so this distance is very large compared to the slit separation. Okay, so since this distance capital D is very large, very far, alright, so S1P, so this point P is somewhere over here. This point P is somewhere over here, very close to point O. Point P will be very close to point O. So therefore, S2P is somewhere over here, S1P is somewhere over here, okay? So therefore, S1P and S2P, they are almost very, similar, almost the same length. And they are in fact almost equal to capital D. So we've considered S1P also, we've approximated S1P also to be capital D and S2P also to be capital D. So therefore D plus capital D becomes 2 into capital D. So 2, they divide each other out, and therefore the path difference, however small a path difference it be, we want to get some value, we want to get some figure for it. So therefore S1P minus S2P becomes XD by capital D. So this is the path difference. This is how we calculate the path difference. Okay. If you check a book, it's given in some other method. All right. If you find that easier, of course, you can stick to that. But calculation of these things, I don't think will come for your exam. But still, you need to remember. You need to know how to calculate. So the path difference between these two waves is x small d divided by capital D. Now, if this path difference is a whole number multiple of lambda, then what we get is, from the condition for constructive interference, if this path difference is a whole number multiple of lambda, then we get a constructive interference at this point. Whereas if this path difference is an odd number multiple of lambda by 2 from the condition for destructive interference, if this path difference is an odd number multiple of lambda by 2, then at this point P, we are going to get a destructive interference. So like I already told you, we'll get constructive interference or bright fringe at point P if this path difference is equal to n lambda, whole number multiple of lambda, and destructive interference if this path difference is an odd number multiple of lambda by 2. Alright, so for the central bright fringe, this at point O, since O is the midpoint on the screen, so therefore we call this a central, bright fringe or central maximum. For central maximum, the path difference is 0. There is no path difference. That is, n has to be 0. So if n is 0, that is the bright fringe for the central maximum. Alright, now what about the first bright fringe? For the first bright fringe, n is equal to 1. That is, the path difference is equal to lambda. So if the path difference is equal to lambda, we get the first bright fringe. Okay? And if the path difference is 2 lambda, that corresponds to the second bright fringe. If path difference 3 lambda corresponds to the third bright fringe, and so on and so forth, remember. Okay, likewise, So this is the condition for the nth bright fringe, so to say. Likewise, for the nth dark fringe, this is the condition. For the first dark fringe, mind you, will be on either side of the center maximum. So you have a center maximum over here. So this is the center maximum. Then on either side of the center maximum, we have a dark fringe like this. We will get a dark fringe like this on either side. Then after, we have the first bright fringe on the upper side, and likewise the first bright fringe on the lower side. Then again we have the second dark fringe. So this, here comes the second dark fringe, and on the lower side also this is the second dark fringe. Okay, on my picture it looks of different lengths, but they are of the same length, remember, which is called fringe width. We are going to talk about that, okay, but they are, of the same length. Every bright fringe, every dark fringe is of the same length. So for the first dark fringe, the path difference xd by capital D has to be equal to lambda by 2. So if xd by capital D is lambda by 2, we get these dark fringes. Understood? So if xd by capital D is 3 lambda by 2, we get the second dark fringe, and so on. So this is the condition for the nth dark fringe, is somewhere, on either side of the bright fringe. Now let us discuss this very important thing, which is called fringe width. Now what is this fringe width? Let's look at its definition first. Fringe width is the distance or the separation between two consecutive bright fringes, or the distance between two consecutive dark fringes. So we have two consecutive dark fringes here. This distance, this separation between them, this distance is what is called fringe width. Okay, likewise below this dark fringe you will have a bright fringe, of course. So the separation between two consecutive bright fringes, this distance, is what is called fringe width, remember. And for interference, the fringe width has a constant value. The distance between two although in my picture this looks smaller, this looks bigger, but they will have the same value. Okay, the separation between two consecutive dark fringes and the separation between two consecutive bright fringes is what is called fringe width. And for interference, this separation and this separation will be the same, and it is generally denoted by a beta. Fringe width is denoted by a beta. Now let's try calculating. What I've done over here is I've done the calculation for fringe width in case of bright fringes. So I have shown here the separation between, how to calculate the separation between two consecutive bright fringes. Okay, now we know the nth bright fringe. For nth bright fringe we have this condition. The path difference has to be equal to n lambda. I have considered this distance xn to be the distance of the nth bright fringe from our central point over here. Okay, so here is our point O, this is the central point O. So I have considered the distance of point P. P is some random point. Okay, the distance of point P from point O to be x. So if P, at point P we have the nth bright fringe, then the separation between the nth bright fringe and our central point O is xn. That is exactly what I've considered. So for nth bright fringe we have this, and thereby xn comes out to be n lambda capital D by small d. Very, very simple mathematics. Likewise, so here we have the nth bright fringe. Above the nth bright fringe we will have a dark fringe. Let me just get that piece of chalk. Okay, so here we have a dark fringe. Now above this dark fringe we have the n plus 1th bright fringe. If this is our nth bright fringe, then this has to be our n plus 1th bright fringe. So we are saying the distance of the nth bright fringe from the central point O is xn. Now the distance of n plus 1th bright fringe from point O will be different, will be more, of course. So that distance we are saying is xn plus 1. That is the distance of our n plus 1th bright fringe from our central point O. So here is our central point O. This distance is xn plus 1. So what is fringe width therefore? The distance between two consecutive bright fringes. N and n plus 1th bright fringes are consecutive bright fringes. So the distance between these two bright fringes will be xn plus 1 minus xn. So if we can calculate xn plus 1 minus xn, that will give us the distance between these two consecutive bright fringes. Alright, so for n plus 1th bright fringe, we have the same condition, xn plus 1, the path difference xn plus 1 small d by capital D has to be equal to n plus 1 into d for n plus 1th bright fringe, and therefore xn plus 1 comes out to be this much, and thereby the fringe width beta will be xn plus 1 minus xn, which is this much, substituting the values, okay, and doing the calculation we get the fringe width, that is the separation between the nth bright fringe and the n plus 1th bright fringe comes out to be lambda capital D by small d. This expression is very, very important for you all. It's extremely very important for you all, because based on this you will get numericals from Young's double slit experiment, also to say from interference of light. We can do similar kind of calculation for a dark fringe also, okay, and we'll see for a dark fringe also we'll get to see beta to be equal to lambda capital D by small d. We'll get the same value for the fringe width in case of dark fringes also. Very quickly, I've shown the calculation here for dark fringes also, fringe width in case of dark fringes also. You can check the mathematics. For nth dark fringe, the path difference xnd by capital D, where xn of course is the position or the distance of the nth dark fringe from our point O. Okay, so xnd by capital D is 2n plus 1 into lambda by 2, thereby xn is this much. Likewise, for n plus 1th dark fringe, the consecutive, dark fringe, n plus 1th dark fringe, we have xn plus 1, d by capital D is 2n plus 1. Instead of n, we have n plus 1 now, okay, because we are talking about the n plus 1th dark fringe. So instead of n, we have n plus 1. Every other thing is the same, plus 1 into lambda by 2. So the fringe width in case of dark fringes will be xn plus 1 minus xn, which is this. You do the mathematics and you will see that the fringe width beta comes out to be lambda capital D by small d. The very same expression, like we've got in case of which we've got in case of the bright fringe as well. So this is a very, very important expression for you all, like I've already told you. The fringe width beta is lambda capital D by small d. Now sometimes you'll also be asked to plot a graph of the intensity versus path difference in case of interference of light. Alright. Now what you will see is, if you're plotting intensity along the y-axis and path difference along the x-axis, so this will be the graph like. That is, this is 0, this is path difference 0, meaning this is the bright fringe. Okay, this is the first bright fringe, this is the second bright fringe on one half, and this is the first bright fringe, the second bright fringe on the lower side or on the other side of the interference pattern, so to say. Okay, so remember, so here this 0, path difference 0 means first bright fringe, path difference lambda by 2 on either side of the central maximum, so to say, we have dark fringe. Path difference lambda, we have the first bright fringe. Path difference 3 by 2, this is the second dark fringe here. And path difference 2 lambda on either side of the central maximum, we have a bright fringe, and so on, it goes on. Alright, and as you can see, all of the bright fringes are equally lit. So to say, in case of interference pattern, you need to understand this very, very carefully. All the bright fringes are equally bright, equally lit, and all the dark fringes are equally dark. These are the two sources, the two slit S1 and S2. The bright fringes will be brighter than your two slits. The bright fringes will be brighter than the two slits. So to say, it's like they're here, when we in the interference pattern we are getting more energy. In the bright fringes, it's more bright, it's brighter than the two slits, means there is more energy over here. So is this a violation of conservation of energy? That's the question. And the answer of course is no. This is not a violation of conservation of energy. It can't be, of course. Okay, conservation of energy can't be violated. So what is happening? Why is this brighter than the slits? Because whatever energy was supposed to reach here, that energy has been, that is at these positions of the dark fringes. Whatever energy was to reach, that energy has shifted to these positions where we have the bright fringes. Okay, so whatever energy was to reach at these positions where we have the dark fringes, those energy has been shifted or focused on the bright fringes itself. So therefore the energy at these positions where we are getting the bright fringes, it's like the energy is doubled at those positions. Okay, so this is not a violation of conservation of energy, and you'll be asked to plot this graph sometimes.